Welcome to Sleepy Science. Tonight we will drift gently through the quiet vastness of the universe. Before we begin, take a moment to relax your mind and settle into a comfortable position. If you enjoy calm explorations of science and space, consider liking the video and subscribing to the channel. And feel free to write in the comments where in the world you are listening from tonight. Somewhere on this planet, people from many different places are looking at the same sky. And together we are all passengers inside a very large and mysterious universe. Tonight our journey moves toward one simple but fascinating question. What is the largest star ever discovered in the universe? The answer may sound simple at first, but as we slowly explore deeper layers of the cosmos, we begin to realize that stars are far more complex and enormous than our everyday imagination can easily grasp. The universe is filled with billions of galaxies, and inside those galaxies exist countless stars. Some are small and quiet. Others are massive blazing giants that stretch across distances that are difficult to truly picture. When we look up at the night sky, the stars appear as tiny points of light scattered across the darkness, calm and distant like small lanterns hanging in space. Yet the truth is that most of those points of light are not small at all. Many of them are enormous spheres of gas burning with incredible energy. Some stars are so large that if they were placed where our sun currently sits, they would stretch far beyond the orbits of several planets. To understand the idea of the largest star, we first need to slowly adjust our sense of scale. The universe operates on sizes that are very different from what we experience in everyday life. On Earth, we measure distances with meters and kilometers. Cities and mountains seem large to us. Oceans feel vast. But when we begin to measure objects in space, those familiar scales become very small. Our own sun already feels enormous when compared with Earth. The sun is so large that more than 1 million Earths could fit inside its volume. Imagine a sphere so large that if Earth were placed inside it again and again, it could repeat this more than 1 million times before the space is filled. Yet, in the wider universe, the sun is actually considered an average-sized star, neither particularly small nor especially large. This realization is often the first moment when people begin to understand how extraordinary the universe truly is. If the sun is average, then there must be stars far larger than it. Stars that expand to sizes so immense that our solar system itself would seem small beside them. These giant stars exist quietly across the galaxy, glowing with deep red light or brilliant blue energy, slowly living out their lives over millions of years. The universe does not rush. Stars are born slowly from clouds of gas drifting through space. They grow, they shine, and eventually they change and fade. But during some stages of their lives, certain stars grow to extraordinary sizes, becoming what astronomers call giant stars and supergiant stars. These are the stars that lead us closer to the question we are exploring tonight. Some of these enormous stars are so large that if one replaced our sun, the outer layers of the star would reach beyond the orbit of Mars. Others could stretch even farther into the solar system, surrounding the paths where our planets currently travel around the sun. Imagining such a scale can feel almost dreamlike, yet these objects truly exist in the universe. Among these giants, there are a few stars that stand out even more. Rare stellar behemoths whose diameters extend for billions of kilometers. Stars so wide that light itself would take many hours just to travel from one side of the star to the other. These extraordinary objects represent some of the largest natural structures that exist as single stars. Astronomers have spent decades observing the sky carefully, measuring the brightness of distant stars, studying their color and temperature, estimating their size through careful calculations and observations, slowly building a catalog of the largest stars known to science. And through this quiet, patient work, one name appears again and again when the conversation turns to the largest stars ever discovered. But before we arrive at that immense cosmic giant, it helps to slowly understand how stars work, why they grow so large, and how scientists measure something that exists thousands of light years away in the darkness of space. Because when we understand those pieces, the true scale of the largest known stars becomes even more fascinating. For now, imagine drifting peacefully through space, far away from Earth, surrounded by silent darkness and distant starlight. Somewhere out there, enormous stars are quietly shining, some of them so vast that our entire solar system would disappear inside them. And as we continue this calm journey through the cosmos, we will begin to discover how these giants form, how they grow, and which star currently holds the title of the largest star ever found. Before we can truly understand the giants of the cosmos, it helps to pause for a moment and simply ask a very basic question. What exactly is a star? When we look up at the night sky, the stars appear small and quiet, like tiny glowing dots scattered across the darkness. But in reality, each one is an enormous sphere of extremely hot gas floating in space, held together by gravity and producing energy deep inside its core. A star is mostly made from hydrogen gas, the simplest and most common element in the universe. When large clouds of hydrogen gather together in space, gravity slowly pulls the gas inward, squeezing it tighter and tighter over long periods of time. As the gas becomes denser and hotter, something remarkable begins to happen deep inside the center of the forming star. The pressure and temperature become so intense that hydrogen atoms begin to fuse together. This process is called fusion, and it is the engine that powers every star in the universe. During fusion, hydrogen atoms combine to form helium, and in the process enormous amounts of energy are released. This energy moves outward through the star and eventually escapes as light and heat. This constant balance between gravity pulling inward and energy pushing outward is what allows a star to exist for millions or even billions of years. Gravity tries to compress the star smaller, while the energy created by fusion pushes the outer layers outward. And when these two forces balance each other, the star remains stable. In many ways, a star is like a giant glowing ball of gas that has reached a delicate equilibrium. Gravity holds the material together, while nuclear fusion produces the light we see from far away across space. This simple balance is the reason stars shine steadily for such long periods of time. Our own sun is a perfect example of this balance. Every second inside the sun, enormous numbers of hydrogen atoms fuse together, producing the light and warmth that reaches Earth. Without this steady process, life on our planet would not exist. Yet despite its importance, the sun is only one of hundreds of billions of stars inside our galaxy. When astronomers study stars, they often look at three main characteristics: the temperature of the star, the brightness of the star, and the size of the star. These properties can vary greatly from one star to another. Some stars burn hotter than others, some shine far brighter, and some grow to sizes that are almost difficult to imagine. Stars also come in different colors depending on their temperature. Cooler stars tend to glow with a soft red or orange light. Stars like our sun appear yellow or white, while the hottest stars shine with a brilliant blue color. These colors tell astronomers a great deal about what is happening inside the star. But the size of a star is where things begin to become especially interesting. Some stars are much smaller than the sun. These are often called dwarf stars, and many of them quietly burn their fuel for extremely long periods of time, sometimes trillions of years, much longer than the current age of the universe. Other stars, however, take a very different path. Instead of remaining modest in size, they expand dramatically during certain stages of their lives. Their outer layers swell outward into space, transforming the star into a giant or even a supergiant star. These are the stars that begin to approach the incredible sizes we are exploring tonight. When a star becomes a giant, its radius can expand hundreds of times larger than it once was. The outer atmosphere becomes more spread out and cooler, often giving the star a deep reddish color when viewed from Earth. These enormous stars glow with a soft crimson light and are among the most visually striking objects in the night sky. Despite their enormous size, many giant stars are actually less dense than smaller stars. Their outer layers are spread across such vast distances that the gas becomes very thin. In some regions, the density can even be lower than the air in Earth's atmosphere. Yet the star still maintains its massive glowing structure through gravity. This combination of immense size and relatively low density is one of the reasons certain stars can grow to such incredible proportions. Their outer layers drift outward slowly, expanding across millions of kilometers into space, creating stellar giants that dwarf our own sun. As astronomers continued to observe the sky over the past century, they began discovering more and more of these enormous stars. Each new observation revealing objects that seemed larger than the last, slowly building a picture of just how extreme stellar sizes can become. Some of these stars are hundreds of times larger than the sun. Others stretch thousands of times wider. And a small number push the limits of what scientists once believed was possible for a star. These rare cosmic giants are the stars that bring us closer to answering our original question. Somewhere among them exists a star so large that if it replaced our sun, the outer edge of the star would extend far beyond the orbit of Jupiter, swallowing the inner planets completely inside its vast glowing atmosphere. A star so immense that the scale almost feels unreal. And as we continue our calm journey deeper into the quiet universe, we begin to see how such stars form in the first place. Because the story of the largest star ever discovered begins long before the star itself exists, inside enormous drifting clouds of gas that slowly give birth to new stars across the galaxy. Far away from the bright lights of cities, deep inside the silent regions of our galaxy, enormous clouds of gas and dust drift slowly through space. These clouds are often so vast that they stretch across dozens or even hundreds of light years, and inside these quiet cosmic structures the story of every star begins, including the enormous stellar giants that astronomers study today. These clouds are called nebulae, and although they appear calm and beautiful when observed through telescopes, they are actually the birthplaces of new stars. Slow-moving environments where gravity patiently gathers material together over incredibly long periods of time. A nebula may contain enormous amounts of hydrogen gas, tiny particles of dust, and traces of other simple elements. The material is spread across huge distances, and at first the gas may seem almost empty. But gravity is always present, gently pulling matter inward, causing small regions inside the cloud to become slightly denser than the surrounding areas. Over thousands and then millions of years, these dense pockets slowly begin to grow as more gas is drawn toward them, forming regions where gravity becomes stronger and stronger. As the gas collapses inward, the material begins to spin and compress. The center of the forming object grows hotter and denser, while the surrounding cloud continues feeding more material toward the middle, slowly shaping what astronomers call a protostar. At this stage, the object is not yet a true star. It does not produce its own energy through fusion. Instead, it glows faintly due to the heat generated by the collapsing gas, quietly warming as gravity continues to squeeze it tighter. Inside the core of this forming star, the temperature gradually climbs higher and higher, reaching millions of degrees. Atoms begin moving faster and faster as the pressure grows more intense. And eventually, a critical moment arrives when hydrogen atoms begin to fuse together, releasing enormous energy. When this process begins, the protostar finally becomes a true star. A new source of light ignites within the darkness of the nebula, and the surrounding gas slowly clears away as radiation and stellar winds push outward. This process of star formation happens across galaxies all the time, in regions where vast clouds of gas slowly collapse and ignite new suns. Sometimes these newborn stars are small and modest, destined to live quiet and extremely long lives as red dwarf stars, burning their fuel slowly for trillions of years. Other stars, however, gather much larger amounts of gas during their formation, growing heavier and more powerful as they ignite. These massive newborn stars burn hotter and brighter, and their lives unfold in a much more dramatic way. When a star forms with a very large amount of mass, its gravity becomes stronger, compressing the core to even higher temperatures. This allows nuclear fusion to proceed at a much faster rate, producing enormous energy and causing the star to shine with intense brightness. These massive stars often appear blue or white when observed through telescopes, their surfaces blazing at temperatures far hotter than our sun. And although they may appear stable, their enormous energy output means they consume their fuel much faster. Ironically, the largest stars in the universe tend to live much shorter lives than smaller stars, because the more massive a star becomes, the faster it burns through its supply of hydrogen fuel. While small stars may survive for trillions of years, very massive stars may exist for only a few million years before they begin to change dramatically. As these large stars evolve, their internal structure slowly transforms. The balance between gravity and energy shifts as the fuel in the core begins to change. New fusion processes occur, heavier elements are formed, and the outer layers of the star respond by expanding outward. Over time, the star can grow far larger than it was when it first formed, its atmosphere swelling into space until the star becomes a true giant among stars. These expanding stars are known as giant stars and supergiant stars. Their surfaces cool slightly as the outer layers spread across enormous distances, often giving the star a deep orange or red color when viewed from Earth. Although the temperature of the outer surface may be lower than before, the total size of the star becomes enormous, sometimes reaching hundreds or even thousands of times the radius of our sun. This transformation is one of the most fascinating stages in the life of a star, because it creates the largest stellar structures that can exist without collapsing under their own gravity. Vast glowing spheres whose outer atmospheres drift across billions of kilometers of space. Inside these stars, the core continues producing energy, while the outer layers remain loosely bound by gravity, forming the gigantic stellar envelopes that astronomers observe from distant telescopes. Many of the largest stars known today belong to this category of red supergiants, enormous stars whose diameters can stretch far beyond the orbit of Mars. If placed at the center of our solar system, these stars glow with a calm reddish light and appear as some of the most luminous objects in the night sky. Yet even among these giants, there are a few rare examples that stand far above the rest. Stars so large that their sheer size pushes the limits of what scientists once believed possible for stellar structures. Discovering these objects required careful observation, patient measurements, and decades of study as astronomers slowly improved their understanding of stellar physics. Through this gradual process, scientists began identifying certain stars whose sizes seemed almost unbelievable. Stars whose outer atmospheres extended for distances so large that comparing them with our sun became almost surreal. Among these stellar giants, astronomers eventually found several candidates that compete for the title of the largest star ever discovered, each one a colossal object shining quietly somewhere within the vast structure of our galaxy. Understanding how such enormous stars exist requires us to first compare them with something familiar. And the most natural place to begin that comparison is with the star closest to us, the sun. Because once we understand the true scale of our own star, the immensity of these cosmic giants becomes far easier to appreciate. Before the mind can fully appreciate the largest stars ever discovered, it helps to pause and carefully examine the scale of the star closest to us, the sun. Because the sun provides the most familiar reference point we have when thinking about stellar size. Everyday sunlight reaches Earth and quietly illuminates the world. Yet the star producing that light is already an object of immense scale, far larger than anything on our planet. The diameter of the sun is about 1,400,000 kilometers, which means it is more than 100 times wider than Earth. And its volume is so enormous that more than 1 million Earth-sized planets could fit inside it. If we imagine placing Earth next to the sun, The comparison quickly becomes striking. Our planet would appear as a tiny sphere beside the vast glowing surface of the sun. Even the largest planets in our solar system look small when compared to this star. Jupiter, the largest planet orbiting the sun, is more than 11 times wider than Earth. Yet the sun is still roughly 10 times wider than Jupiter. These comparisons already reveal how large a typical star can be. Yet, in the universe, the sun is considered a rather ordinary example. Astronomers classify the sun as a medium-sized star, sometimes referred to as a yellow dwarf star, which simply means it is a stable star of moderate mass and temperature that produces energy steadily through hydrogen fusion in its core. Stars like the sun are common throughout the galaxy, quietly shining for billions of years while maintaining a relatively stable size and brightness. Our sun has already existed for about 4.5 billion years and will likely continue shining for several billion more before it eventually begins to change. The important realization here is that although the sun feels enormous from our human perspective, it is not among the largest stars in space, not even close. When astronomers began studying other stars in detail, they quickly discovered many that were far larger and far brighter than the sun. Some of these stars were only a few times larger, while others expanded to sizes that seemed almost impossible when compared with the familiar scale of our solar system. To understand how these enormous stars compare with the sun, scientists often use a measurement called solar radius, which simply means the radius of the sun used as a unit of measurement. If a star has a radius 10 times larger than the sun, it is described as 10 solar radii. If it has a radius 100 times larger, it is described as 100 solar radii. This simple method allows astronomers to compare stars across the galaxy using the sun as a universal reference point. Some giant stars reach sizes of several hundred solar radii, which already means they are hundreds of times larger than the sun. If such a star were placed at the center of our solar system, its outer layers could extend past the orbit of Mercury and perhaps even Venus. These stars represent the first step into the category of stellar giants, objects whose atmospheres swell far beyond the scale of ordinary stars. But as astronomical observations improved, scientists began discovering stars that were even larger than these giants. Certain red supergent stars were measured at sizes reaching more than 1,000 solar radii. At this scale, the comparison becomes almost surreal, because if such a star replaced the sun, its outer layers would stretch beyond the orbit of Mars, filling a huge portion of the inner solar system with glowing stellar gas. The reason these stars grow so large is connected to changes occurring deep inside their cores. As a star ages, the hydrogen fuel in the central region slowly becomes depleted. The balance between gravity and energy production begins to shift, and the star responds by expanding its outer layers outward into space. The surface temperature of the star may actually decrease slightly during this process, which is why many of the largest stars appear reddish in color. Yet the overall size of the star becomes vastly greater. This stage of stellar evolution produces some of the most visually impressive stars known to astronomy, the red supergiants. These stars glow with a deep reddish light and often appear slightly unstable, their outer atmospheres expanding and contracting over time, sometimes shedding large amounts of gas into the surrounding space. Despite their calm appearance from Earth, these stars are incredibly dynamic environments with enormous internal energy. Among the red supergiants, astronomers have discovered several stars whose sizes stretch the limits of stellar physics. These stars can be more than 1,000 times wider than the sun, meaning their diameters extend across billions of kilometers. Trying to imagine such a scale requires stepping far beyond everyday experience, because these stars are so large that light itself needs many hours to travel from one side of the star to the other. For comparison, light travels around the entire Earth more than 7 times in a single second. Yet crossing the diameter of one of these stellar giants could take several hours even at the speed of light. This simple fact helps reveal just how enormous these objects truly are. Observations of these stars often require extremely powerful telescopes and careful analysis of their brightness and distance. Astronomers measure how much light a star produces, determine how far away it is from Earth, and combine this information with models of stellar atmospheres to estimate the radius of the star. Through these methods, scientists slowly build a clearer picture of the largest stars that exist in our galaxy. Over time, a few specific names began appearing repeatedly in astronomical studies whenever scientists discussed extremely large stars. These stars became famous among astronomers because their estimated sizes placed them among the most enormous stellar objects ever observed. Some of these giants reside thousands of light years away, inside dense regions of the Milky Way galaxy, shining quietly in distant star clusters where massive stars are more likely to form. Hidden among these regions are some of the largest stars ever measured, stars whose diameters reach thousands of times larger than the Sun. Among these remarkable objects, a few stand out as especially important when discussing the largest star ever discovered. And understanding their characteristics brings us closer to answering the central question of this calm cosmic journey. As we continue drifting through the quiet scale of the cosmos, it becomes natural to ask another gentle question. Why are stars so different in size? Why does one star remain modest and stable for billions of years, while another grows into a colossal giant that stretches across unimaginable distances? The answer lies in a combination of factors that shape every star from the moment it is born, including the amount of material it gathers, the balance of gravity inside it, and the slow changes that happen throughout its lifetime. When a star first forms inside a nebula, the amount of gas that gathers into the collapsing core determines the mass of the newborn star. Some stars form with relatively small amounts of material and become small red dwarf stars, quiet and efficient objects that burn their fuel slowly and steadily. Other stars gather far larger amounts of gas during formation, becoming massive stars whose strong gravity compresses their cores to extreme temperatures. These massive stars burn their fuel much faster and shine with intense brightness. The mass of a star is therefore one of the most important properties that determine how the star will evolve over time. Small stars live very long lives and change slowly, while massive stars live shorter and more dramatic lives, expanding, transforming, and sometimes ending in powerful explosions. Because of this difference, the largest stars we observe today usually began their lives with far more mass than the Sun. Inside a massive star, the strong gravitational pressure pushes the core to extremely high temperatures, allowing fusion reactions to occur more rapidly. Hydrogen is converted into helium at a much faster rate than in smaller stars, producing enormous energy that pushes outward through the star. This intense energy output causes the outer layers of the star to become unstable over time, gradually expanding farther and farther into space. As the star ages, the hydrogen fuel in its core slowly becomes depleted, and when this happens, the inner balance of the star begins to change. Gravity compresses the core even further, while new fusion reactions begin in surrounding layers. These internal changes cause the outer atmosphere of the star to swell outward dramatically, transforming the star into a giant or supergiant star, whose size may be hundreds or even thousands of times larger than its original state. Another interesting factor influencing the size of stars is the temperature of their outer layers. When a star expands, its surface temperature often decreases slightly because the same energy is now spread across a much larger surface area. This cooling causes the star to glow with a reddish color rather than the bright yellow or white color seen in stars like the Sun. For this reason, many of the largest stars in the universe are known as red supergiants. Red supergiants are fascinating objects because their enormous size does not always mean they contain vastly more material than smaller stars. In fact, the gas in their outer layers is often extremely thin and spread across vast distances. If one could somehow float through the outer atmosphere of such a star, The density of gas might feel almost like a vacuum compared to conditions on Earth. Despite this low density, the total volume of these stars becomes enormous. Their atmospheres can extend across billions of kilometers, forming giant, glowing spheres that dominate their surrounding regions of space. Observing these stars through telescopes often reveals subtle variations in brightness and color as the outer layers slowly move and shift over time. Some of the largest stars also lose material gradually through powerful stellar winds. These winds push gas away from the surface of the star and send it drifting into the surrounding space, creating enormous clouds of glowing material around the star. Over thousands of years, these clouds can expand into beautiful structures known as nebulae, gently illuminated by the light of the star at the center. Because massive stars lose material and change rapidly, their lives are much shorter than those of smaller stars. While the sun may continue shining for about 10 billion years, a very massive star may only live for a few million years before reaching the final stages of its life. In cosmic terms, this is an extremely short lifetime, meaning that the largest stars we observe today are relatively rare. Astronomers therefore search carefully across regions of the galaxy where massive stars are more likely to form. These regions often include dense star clusters, where large clouds of gas once collapsed to form many stars at roughly the same time. Inside these clusters, scientists sometimes find enormous red supergiant stars shining quietly among thousands of smaller stars. Each time astronomers discover one of these stellar giants, they measure its brightness, estimate its temperature, and calculate its radius using detailed models of stellar atmospheres. Through decades of observation, scientists have gradually identified a handful of stars whose estimated sizes push the boundaries of what a star can become. Among these discoveries, certain stars have gained particular attention because their diameters appear almost unbelievably large. These stars are often located thousands of light years away, hidden within distant star clusters or deep regions of the Milky Way galaxy. Their light travels across space for thousands of years before finally reaching Earth, allowing astronomers to study them with modern telescopes. The story of the largest star ever discovered slowly emerges from these careful observations. As scientists compare the sizes of different red supergiants and determine which one stretches the farthest across space, several candidates compete for this remarkable title, each one an enormous sphere of gas whose outer atmosphere extends across billions of kilometers. Understanding these giants requires patience and imagination, because their scale goes far beyond the familiar world of planets and moons. Yet as we continue this calm journey through the universe, we begin to see how these colossal stars fit into the larger story of stellar evolution and cosmic structure. Once the scale of stars begins to settle gently in the mind, it becomes easier to imagine how enormous some of the giants of the universe truly are. The sun already feels immense when compared with Earth, yet when astronomers began carefully measuring other stars, they discovered many that were far larger. These stars belong to a category often called giant stars and supergiant stars, and they represent some of the most impressive objects that exist in the cosmos. A giant star forms when an ordinary star begins to age and its internal balance slowly changes. As hydrogen fuel in the core decreases, the star responds by expanding its outer layers outward into space. This transformation can increase the size of the star dramatically. A star that once had a size similar to the sun may eventually grow dozens or even hundreds of times larger. The surface of the star becomes cooler during this expansion, often glowing with a deep orange or red color when seen from Earth. Supergiant stars take this process even further. These stars are among the largest and brightest stars in the universe. Their radii can extend hundreds or thousands of times the radius of the sun. When astronomers first realized that stars of this size existed, it was almost difficult to believe, because the scale is so extreme that normal comparisons begin to lose meaning. To understand this scale, imagine placing a supergiant star where our Sun currently sits at the center of the solar system. The inner planets would disappear completely inside the star. Mercury would be swallowed first, then Venus, and even Earth could end up deep inside the outer layers of the star. In some cases, the star might expand far enough to reach the orbit of Mars, turning much of the inner solar system into a glowing sea of hot stellar gas. One of the interesting aspects of these stars is that their enormous size does not always mean they are extremely dense. In fact, many supergiant stars have outer atmospheres that are very thin and extended. The gas spreads across such a vast region that the density becomes incredibly low. Yet gravity still holds the star together as a massive sphere of glowing material. Because these stars are so large, their surfaces behave in ways that are very different from smaller stars. Instead of a stable surface like the Sun, many supergiants have enormous convection currents. These are giant movements of hot gas rising and falling across the surface. Each of these convection cells can be so large that it could cover an area bigger than the entire orbit of Earth. The surface of a supergiant star is therefore constantly shifting and changing as these massive flows of gas move slowly across the star. Astronomers observing these stars often notice variations in brightness that occur over months or years. These changes happen because the outer layers of the star expand and contract slightly as energy moves through the interior. The atmosphere of the star may pulse gently, growing larger and then slightly smaller again. These slow rhythms add another layer of complexity to the lives of giant stars. Many of the most famous giant stars visible from Earth belong to the category known as red supergiants. These stars shine with a calm reddish glow and are often located within familiar constellations. Their color comes from the cooler temperature of their expanded outer layers. Although cooler does not mean cold in human terms, the surfaces of these stars are still thousands of degrees hot. Red supergiants represent one of the final stages in the life of a very massive star. As the star continues evolving, deeper processes occur inside its core. New elements begin forming through fusion, heavier atoms appear, and the internal structure becomes more complex. While these changes occur deep inside the star, the outer atmosphere continues drifting outward, creating the vast size that makes these stars so remarkable. Through telescopes, astronomers can observe these distant giants and estimate their sizes by studying their brightness and temperature. By combining these observations with models of how stars behave, scientists can calculate the approximate radius of the star. Over many years of careful observation, a list of extremely large stars has gradually emerged. Among these stars, several names appear repeatedly when scientists discuss the largest stars known to exist. Some of these stars are already famous among astronomy enthusiasts because their size pushes the boundaries of what we expect a star to be. They are often located thousands of light years away and shine quietly among dense regions of the Milky Way galaxy. One such example is a red supergiant star located in the constellation Scorpius, known as Antares. This star is hundreds of times larger than the Sun and glows with a deep red color that makes it one of the brightest stars in the night sky. Another well-known example is Betelgeuse in the constellation Orion, a star whose enormous size has fascinated astronomers for generations. Yet even these impressive stars are not the largest that scientists have discovered. As telescopes improved and measurements became more precise, astronomers began identifying stars that were even larger than these famous giants. Some of these stars extend far beyond 1,000 times the radius of the Sun, becoming true titans of the stellar world. These discoveries slowly brought scientists closer to identifying the largest stars ever observed. Among them are a few extraordinary objects whose estimated sizes stretch across distances so vast that imagining them requires stepping far beyond the scale of our solar system. These stars represent the upper limits of how large a star can grow before gravity and stellar physics begin to impose natural boundaries. Understanding these giants leads naturally toward the most famous of the enormous stars discovered so far. Stars whose diameters reach billions of kilometers and whose presence in the galaxy reveals just how astonishing the universe can be. As astronomers continued observing the sky and measuring the properties of distant stars, a particular category of stars began to attract special attention. These stars were enormous, glowing with a deep red light and expanding to sizes far beyond ordinary stars. These objects became known as red supergiant stars, and they represent some of the largest stars that can exist in the universe before reaching the final stages of stellar evolution. A red supergiant is a star that has grown to an extraordinary size during the later part of its life. After spending millions of years burning hydrogen in its core, the star begins to change internally. The balance between gravity and energy slowly shifts as the hydrogen fuel becomes less abundant in the center. Gravity compresses the core further and new fusion reactions begin occurring in layers surrounding the core. These changes release large amounts of energy and cause the outer atmosphere of the star to expand outward dramatically. As the star expands, its surface spreads across a much larger region of space. The same energy that once radiated from a smaller surface now spreads over a larger area, which causes the surface temperature to decrease slightly. Because of this cooling, the star begins to glow with a reddish color rather than the bright yellow or white color seen in stars like the sun. This deep red glow is one of the defining features of red supergiant stars. Despite the cooler surface temperature, the total size of these stars becomes astonishing. Some red supergiants reach sizes hundreds of times larger than the sun, while others expand to more than 1,000 times the solar radius. At these scales, the outer atmosphere of the star stretches across distances of billions of kilometers. These stars become enormous spheres of glowing gas whose boundaries are difficult to imagine in everyday terms. If one of these stars replaced the sun at the center of our solar system, the transformation would be dramatic. Mercury, Venus, and Earth would vanish deep inside the outer layers of the star. The glowing atmosphere would extend far into the solar system, surrounding the space where planets once orbited. In the case of some of the largest red supergiants, the star could even reach beyond the orbit of Mars. Another remarkable aspect of red supergiants is the structure of their surfaces. Unlike smaller stars that appear relatively smooth and stable, the surfaces of red supergiants are extremely dynamic. Giant convection currents move hot gas from deep inside the star toward the surface while cooler gas sinks back inward. These flows create enormous regions on the surface where the brightness and temperature vary slightly over time. Some of these convection cells are so large that each one could extend across distances comparable to the orbit of Earth. The surface of a red supergiant is therefore constantly shifting and evolving as enormous currents of gas move slowly across the star. Astronomers observing these stars often detect slight changes in brightness that occur over weeks, months, or even years. Red supergiants also lose material steadily through powerful stellar winds. Gas from the outer layers escapes the gravitational pull of the star and drifts outward into surrounding space. Over thousands of years, this material can form enormous clouds of gas and dust around the star, creating beautiful nebula-like structures illuminated by the light of the star itself. These expanding clouds reveal that red supergiants are approaching the final stages of their existence. Massive stars evolve quickly compared with smaller stars. After only a few million years, the internal processes inside the star eventually lead to a dramatic ending. The core may collapse suddenly, and the star can explode in a powerful event known as a supernova, releasing enormous energy and scattering heavy elements into space. Before reaching that final stage, however, red supergiants spend a relatively short but spectacular period as some of the largest stars in the universe. During this phase, their immense size and brightness make them visible across vast distances in the galaxy. Even though they may be thousands of light years away, their light can still be detected by telescopes on Earth. Many famous stars in the night sky belong to this category. Betelgeuse, located in the constellation Orion, is one of the most well-known red supergiants visible from Earth. Another example is Antares in the constellation Scorpius, a deep red star that shines brightly in the summer sky. Both of these stars are far larger than the Sun and represent impressive examples of stellar expansion. Yet, as remarkable as these stars are, they still may not be the largest known stars in the universe. Continued observations have revealed even more extreme examples, hidden deeper within the Milky Way galaxy. Some of these stars exist in distant clusters where massive stars formed together long ago, and among them astronomers have identified objects whose sizes push the boundaries of stellar physics. These rare stellar giants have diameters so vast that comparing them with the Sun almost feels abstract. Their atmospheres extend across billions of kilometers, and their light travels across thousands of years of space before reaching Earth. These stars represent the upper extremes of what a star can become. Among the many red supergiants discovered over the past decades, a few have become especially famous because of their enormous estimated sizes. Studying these stars allows astronomers to understand the limits of stellar growth and brings us closer to identifying which star might truly be the largest ever discovered in the universe. Among the many red supergiant stars that astronomers have studied over the past century, one of the most recognizable is Antares, a star that glows with a deep reddish light in the constellation Scorpius. When observed from Earth, it appears as a bright red point in the night sky, calm and steady. Yet the object producing that light is far larger and more powerful than our Sun. Antares is located hundreds of light years away from Earth, and even at that great distance, its brightness allows it to stand out among the surrounding stars. The name Antares has an interesting origin. It comes from ancient Greek words meaning rival of Mars. Early observers noticed that the color of this star strongly resembles the reddish appearance of the planet Mars when seen in the night sky. Because of this similarity, the star was given a name that reflected its visual resemblance to the red planet. Long before modern telescopes existed, people had already recognized the striking color of this distant star. Modern astronomy has revealed much more about Antares than ancient observers could ever imagine. Careful measurements of its brightness and temperature have allowed scientists to estimate its size, and the results show that Antares is truly enormous. The radius of Antares is hundreds of times larger than the radius of the Sun. In other words, the star is hundreds of times wider than the star that warms our own planet. If Antares were placed at the center of our solar system, its outer layers would extend far beyond the orbit of Mars. The inner planets would be completely swallowed inside the vast atmosphere of the star. Even the asteroid belt that lies between Mars and Jupiter could fall within the outer regions of the star. Imagining this scale helps illustrate just how immense Antares truly is. Despite its massive size, Antares does not contain a proportionally massive amount of material compared with its enormous volume. Like many red supergiants, the outer atmosphere of Antares is extremely diffuse. The gas spreads across such an immense region that the density becomes very low. Yet gravity still holds the entire structure together as a glowing sphere of hot gas. The surface of Antares is not calm and uniform like the surface of smaller stars. Instead, it is dominated by huge movements of gas rising and falling through the atmosphere. These convection currents transport energy from deep inside the star toward the outer layers. Each rising bubble of hot gas can span an enormous region, sometimes comparable to the size of planetary orbits. The surface of the star slowly shifts and changes as these giant currents move through the stellar atmosphere. Astronomers observing Antares have noticed that its brightness can vary slightly over time. These changes happen because the outer layers of the star gently expand and contract, responding to internal processes occurring deep within the star. This slow pulsation is common among red supergiants and provides important clues about the internal structure of these enormous stars. Another fascinating feature of Antares is the cloud of gas and dust that surrounds it. Because the star is losing material through strong stellar winds, its outer layers are gradually drifting away into space. This escaping gas forms a faint envelope around the star, illuminated by the star's own reddish light. Over long periods of time, this material will spread farther into the surrounding region of the galaxy. Stars like Antares represent an important stage in the life of massive stars. They have already passed through the earlier phases of stellar evolution and have now expanded into their giant form. Deep inside the core, the star continues to produce energy through fusion reactions that involve heavier elements than hydrogen. These internal changes drive the expansion of the star and shape its enormous size. However, even a star as large as Antares is not permanent. Massive stars evolve quickly, compared with stars like the Sun. Over time, the internal structure of the star will continue to change until eventually the core can no longer support the weight of the outer layers. When that moment arrives, the star may collapse and explode in a supernova event, briefly becoming one of the brightest objects in the galaxy. For now, Antares continues shining quietly in the constellation Scorpius, a distant red beacon marking the presence of one of the largest stars visible from Earth. Its enormous atmosphere extends across hundreds of millions of kilometers, glowing softly against the dark background of space. Yet as impressive as Antares is, it does not hold the title of the largest star known to science. As astronomers explored deeper regions of the Milky Way and studied other red supergiants, they discovered stars that grow even larger than this famous giant. Some of these stars expand to sizes so vast that they dwarf Antares itself. One of the most well-known examples of such a star lies within another familiar constellation visible from Earth. A star whose dramatic size and unusual behavior have fascinated astronomers for many years. This star is known as Betelgeuse, and its immense scale offers another step toward understanding the largest stars ever discovered in the universe. Another remarkable red supergiant star that has fascinated astronomers and skywatchers for centuries is Betelgeuse, a bright star located in the constellation Orion. Orion is one of the most recognizable constellations in the night sky, and Betelgeuse forms the glowing reddish shoulder of the giant hunter figure imagined in ancient star maps. Even without a telescope, Betelgeuse can easily be seen with the naked eye, shining with a warm orange-red color that hints at the immense star behind that distant light. Betelgeuse lies hundreds of light years away from Earth, yet despite that distance, its brightness allows it to stand out clearly among the stars surrounding Orion. The reason it shines so strongly is not only because it produces a large amount of light, but also because of its extraordinary size. Betelgeuse is one of the largest stars that can be observed relatively easily from Earth, and for many years it has served as one of the most famous examples of a red supergiant star. When astronomers measure the radius of Betelgeuse, they estimate that it is hundreds of times larger than the Sun. The exact size can vary depending on how the outer atmosphere of the star is defined, because the outer layers are not sharply separated from space. Instead, the atmosphere gradually fades outward into surrounding gas. Even with these uncertainties, it is clear that Betelgeuse is an enormous stellar object whose diameter stretches across hundreds of millions of kilometers. To imagine this scale, it helps to picture Betelgeuse placed at the center of our solar system. In that scenario, Mercury, Venus, Earth, and Mars would all be located inside the outer atmosphere of the star. The glowing red gas would extend outward across much of the inner solar system. The orbit of Jupiter might lie just beyond the outer edge, depending on the exact size of the star at that moment. Betelgeuse is also interesting because it is a variable star, meaning its brightness changes slightly over time. These variations occur because the outer layers of the star expand and contract slowly. The star pulses gently as energy moves through its interior. These pulsations can cause the brightness of Betelgeuse to rise and fall over periods of months or years. In recent years, Betelgeuse attracted global attention when astronomers noticed an unusual dimming event. For a period of time, the star became significantly fainter than usual, leading to speculation that it might be approaching the final stage of its life. Later studies suggested that the dimming was caused by a large cloud of dust released from the star itself, which temporarily blocks some of the light reaching Earth. Events like this reveal that the atmosphere of Betelgeuse is extremely dynamic. Massive flows of gas rise and fall through the star's outer layers, carrying material outward into space. These giant convection currents are far larger than anything seen on smaller stars. Each rising region of hot gas can span distances comparable to the entire orbit of Earth. Because the star is so large, its surface appears uneven when observed with advanced telescopes. Astronomers have actually been able to capture images that show irregular bright and dark regions across the surface of Betelgeuse. These patterns represent enormous regions where hot gas is rising toward the surface or cooler gas is sinking deeper into the star. Betelgeuse is also losing mass gradually through powerful stellar winds. Streams of gas escape the star's gravity and drift into the surrounding region of space. Over thousands of years, these materials accumulate around the star and form large clouds of dust and gas illuminated by the star's reddish light. This material will eventually become part of the interstellar environment of the galaxy. Like other massive red supergiants, Betelgeuse is nearing the end of its life cycle. Deep inside its core, heavier elements are forming through successive fusion processes. Eventually, the star will reach a stage where the core can no longer support the weight of the outer layers. When that moment arrives, the star may collapse suddenly and explode in a spectacular supernova. If Betelgeuse were to explode as a supernova, it would become incredibly bright in Earth's sky for a short period of time. Some estimates suggest it could briefly shine almost as brightly as the moon. Such an event would be visible even during the daytime before gradually fading over the following weeks and months. For now, however, Betelgeuse continues its quiet existence as one of the most impressive stars visible from Earth. Its enormous size and dynamic atmosphere make it one of the most studied red supergiants in astronomy. Yet despite its fame, Betelgeuse is still not the largest star known to science. As astronomers explored deeper regions of the Milky Way galaxy, they discovered even more extreme stellar giants hidden among distant star clusters. Some of these stars grow to sizes far beyond that of Betelgeuse. Their diameters stretch across distances so vast that comparing them with familiar stars becomes increasingly astonishing. Among these colossal objects, scientists eventually identified a star whose size pushed the limits of what had previously been imagined for a star. This star would become one of the most famous candidates for the largest known star in the universe, a red supergiant whose immense atmosphere extends across a distance that is almost difficult to comprehend. Far deeper within the Milky Way galaxy, hidden among dense star fields and distant stellar clusters, astronomers discovered a star whose size pushed the imagination far beyond the already enormous scale of stars like Antares or Betelgeuse. This star is known as Uae-Scuti, and for many years, it has been considered one of the largest stars ever measured. The light from Uae-Scuti travels thousands of years through space before reaching Earth, meaning the star we observe today appears as it existed long before human civilization even began. Uae-Scuti is located in a region of the sky near the constellation Scutum, a relatively small constellation that lies along the dense band of the Milky Way. This region contains enormous numbers of stars, gas clouds, and clusters that make astronomical observation both fascinating and challenging. Within this crowded area, astronomers carefully studied the brightness and temperature of Uae-Scuti and gradually realized that it belonged to the rare category of extremely large red supergiant stars. When scientists estimated the radius of Uae-Scuti, the results were astonishing. The star was calculated to be more than 1,000 times larger than the Sun. In many estimates, its radius reaches around 1,700 solar radii. Numbers like these may sound abstract at first, but when translated into real distances, they reveal the extraordinary scale of the star. The diameter of Uae-Scuti stretches across billions of kilometers. Light itself would need many hours to travel from one side of the star to the other. To visualize this scale, imagine placing Oiskudi at the center of our solar system. In that scenario, Mercury, Venus, Earth, and Mars would vanish completely inside the enormous atmosphere of the star. The outer layers would extend beyond the orbit of Jupiter and approach the distance where Saturn travels around the Sun. This comparison helps illustrate why Oiskudi captured so much attention among astronomers. It represented a star so large that it could easily contain the entire inner solar system inside its glowing atmosphere. The idea of such a massive star existing in reality feels almost dreamlike when compared with the familiar scale of planets and moons. Despite this immense size, Oiskudi does not contain a proportionally huge amount of mass compared with its volume. Like other red supergiants, its outer atmosphere is extremely diffuse. The gas spreads across such a vast region that the density becomes incredibly low. If it were somehow possible to travel through the outer layers of this star, the gas might feel thinner than the atmosphere of Earth. This low density is one of the reasons such stars can grow to these incredible sizes. Their outer layers expand outward and become loosely bound by gravity. The star continues shining because the core deep inside still produces energy through fusion reactions involving heavier elements. Observations of Oiskudi also reveal that its brightness changes slightly over time. These variations occur because the star expands and contracts slowly in a process known as stellar pulsation. The enormous atmosphere gently shifts and moves as energy travels outward from the core through the extended layers of gas. Because the star is so distant, astronomers cannot easily observe fine details on its surface. Instead, they rely on careful measurements of brightness, color, and spectral patterns to estimate the properties of the star. By studying how the star emits light at different wavelengths, scientists can estimate its temperature and determine how large the star must be to produce the observed brightness. These techniques have allowed astronomers to place Oiskudi among the largest known stars in the galaxy. For a long time, it was widely described as the largest star ever discovered. Its enormous radius made it a powerful example of just how far stellar expansion can go during the life of a massive star. However, astronomy is always evolving as new observations are made and new data becomes available. In recent years, scientists studying distant star clusters have identified other red supergiant stars whose estimated sizes may rival or even exceed that of Oiskudi. These discoveries show that the universe still holds many surprises when it comes to the true limits of stellar size. Even so, Oiskudi remains one of the most impressive stars ever studied. Its enormous atmosphere stretches across distances that dwarf the scale of our solar system. The star shines quietly thousands of light years away, a massive sphere of gas glowing with a deep reddish light in the distant regions of the Milky Way. Studying such stars allows astronomers to understand how massive stars evolve and how the largest stellar structures form in the universe. Each observation helps refine our understanding of stellar physics and reveals how gravity, energy, and matter interact on scales far larger than anything found within our solar system. Yet as astonishing as Oiskudi is, the search for the absolute largest star does not end there. Deeper within the galaxy, astronomers have discovered another remarkable star inside a distant cluster, a star whose estimated size may be even greater. This colossal object has become one of the most intriguing candidates for the largest star currently known in the universe. Understanding the true scale of Oiskudi requires slowing down for a moment and gently expanding the imagination, because the numbers used to describe this star are far beyond everyday experience. When astronomers say that Oiskudi may reach roughly 1,700 times the radius of the Sun, the statement sounds impressive, yet the mind often struggles to visualize what that actually means in physical space. To truly appreciate the size of this star, it helps to imagine the solar system itself as a measuring tool. The Sun sits quietly at the center of our solar system, while the planets travel around it in wide circular paths. Mercury completes its orbit in about 88 days. Venus moves along a slightly wider path, and Earth travels at a comfortable distance where liquid water can exist. Beyond Earth lies Mars, then the asteroid belt, and farther outward the giant planet Jupiter begins the region of the outer solar system. If Uiscuti were placed at the center of this system, the scene would change dramatically. The enormous atmosphere of the star would expand outward across billions of kilometers. Mercury would be deep inside the glowing gas. Venus would also disappear within the star, and Earth would no longer orbit a star, but would instead exist inside its outer layers. Mars would vanish as well, surrounded by the extended atmosphere of the giant star. The expansion would continue outward beyond the asteroid belt. In many estimates, the outer layers of Uiscuti could reach near the orbit of Jupiter. This means that nearly the entire inner region of the solar system would be swallowed by the star. Imagining the familiar planets inside the atmosphere of a single star helps reveal just how extraordinary these stellar giants truly are. Another way to understand this scale is to consider how long light would take to travel across the star. Light moves at an incredible speed, crossing the entire Earth more than 7 times in a single second. Yet even at that speed, traveling across Uiscuti would take several hours. A beam of light leaving one side of the star would continue traveling through the star's enormous atmosphere for hours before reaching the opposite side. This immense size also creates unusual conditions in the outer layers of the star. The gas there is extremely thin and extended. Instead of a sharp surface like a solid object, the boundary of the star gradually fades into surrounding space. Astronomers often describe the radius of such stars using models that estimate where the atmosphere becomes transparent enough for light to escape. Inside the star, however, the environment becomes far more extreme. Deep within the core, the pressure and temperature remain incredibly high. Fusion reactions involving heavier elements continue producing energy that slowly moves outward through the massive layers of the star. This energy supports the enormous atmosphere and prevents the star from collapsing under its own gravity. Because Uiscuti is so large, its outer layers are not stable in the same way as smaller stars. The atmosphere gently shifts and moves as giant convection currents transport energy upward. These flows of gas can cover regions larger than entire planetary systems. The star slowly breathes in a sense, expanding and contracting slightly over time as internal energy moves through the enormous envelope. Astronomers studying Uiscuti also observe variations in brightness that occur over long periods. These variations are typical of large red supergiants and reveal that the outer atmosphere of the star is constantly changing. The star may brighten slightly when the outer layers contract and dim again when the atmosphere expands outward. Another fascinating feature of stars like Uiscuti is the gradual loss of material into surrounding space. Powerful stellar winds push gas away from the star and send it drifting into the interstellar environment. Over time, these escaping layers form vast clouds of gas and dust around the star. These clouds may eventually mix with other material in the galaxy and contribute to the formation of future stars and planets. Even though Uiscuti is enormous, it is not necessarily the most massive star known. Size and mass are not always directly connected in the universe. A star can expand to an enormous radius while having a relatively moderate mass compared with smaller but denser stars. This happens because the outer layers become extremely diffuse and spread across enormous distances. This distinction helps explain why the largest stars often appear as red supergiants with extended atmospheres. The low density of their outer layers allows them to expand dramatically without requiring an equally dramatic increase in mass depth. Gravity still holds the star together, while the outer atmosphere spreads outward like a vast glowing cloud. For many years, Uiscuti stood as one of the most impressive examples of stellar expansion ever observed. Its enormous radius made it a powerful symbol of how extreme the universe can be. Yet astronomical research never truly stops. As telescopes improved and scientists studied more distant star clusters, new discoveries began to challenge the idea that Uy might be the absolute largest star. Within a distant cluster deep in the Milky Way, astronomers identified another extraordinary red supergiant whose estimated size may rival or even exceed that of Uy. This star belongs to a group of massive stars located thousands of light years away, and among them lies one of the most fascinating candidates for the largest star currently known to science. Deep within the Milky Way galaxy there exists a distant star cluster known as Stephenson 2, a dense gathering of massive stars located thousands of light years away from Earth. This cluster lies in a region of space where enormous stars formed together from the same giant cloud of gas long ago. Among the many stars shining inside this cluster, astronomers eventually identified one extraordinary object that quickly attracted attention because of its remarkable size. This star is known as Stephenson 218. Stephenson 218 is a red supergiant star, belonging to the same general family as other giant stars like Betelgeuse and Antares, yet its estimated size places it among the most extreme stars ever observed. When astronomers studied its brightness and temperature, they realized that this star might be even larger than many of the previously known stellar giants. Calculations suggested that its radius could exceed 2,000 times the radius of the Sun. To understand the scale of such a star, it again helps to imagine placing it at the center of our solar system. If Stephenson 218 replaced the Sun, its enormous atmosphere would stretch outward across billions of kilometers. Mercury, Venus, Earth, and Mars would disappear completely inside the star. The expanding atmosphere could extend past the orbit of Jupiter and approach the region where Saturn travels around the Sun. Much of the solar system that we know would exist inside the outer layers of this colossal star. These comparisons help reveal why Stephenson 218 has become one of the most important candidates for the title of the largest known star. Its estimated diameter is so vast that even compared with Uy, it appears astonishing. The outer atmosphere of the star extends across distances that challenge the imagination when compared with familiar cosmic structures. However, measuring the size of stars like Stephenson 218 is not a simple task. These stars are extremely far away, and their outer atmospheres do not have a sharp edge that can be easily defined. Instead, the atmosphere gradually fades outward into surrounding space. Astronomers must therefore rely on models that estimate where the visible light of the star is being emitted from the atmosphere. By analyzing the spectrum of light from the star and combining this information with estimates of its distance, scientists can approximate the temperature and luminosity of the star. These values allow researchers to calculate the likely radius of the star. While these estimates carry some uncertainty, they still indicate that Stephenson 218 belongs among the largest stars known to exist. The environment surrounding this star is also fascinating. Stephenson 218 resides inside a cluster filled with other massive stars that formed during the same period of stellar birth. These stars share similar ages and compositions because they originated from the same giant molecular cloud. Studying clusters like Stephenson 2 helps astronomers understand how massive stars evolve together over time. Inside the core of Stephenson 218, intense fusion reactions continue producing energy. The star is likely in a late stage of stellar evolution, where heavier elements are forming deep within its core. As these internal processes unfold, the outer atmosphere of the star has expanded into the enormous red supergiant structure we observe today. The surface of the star is not smooth or stable. Like other red supergiants, it likely contains enormous convection currents, where hot gas rises toward the surface, while cooler gas sinks deeper into the star. Each of these rising regions could be vast enough to cover areas larger than the entire orbit of Earth. The atmosphere therefore moves slowly and continuously as energy travels outward through the star. Stars of this size also lose material steadily through stellar winds. Gas from the outer layers escapes the star and drifts into surrounding space. Over thousands of years, this material can form enormous clouds around the star. contributing new elements to the interstellar environment of the galaxy. These elements may eventually become part of future stars, planets, and perhaps even living worlds. Despite its enormous size, Stephenson 218 will not exist forever. Massive stars evolve quickly on cosmic timescales. Eventually, the core of the star will reach a stage where it can no longer support the weight of the outer layers. When this moment arrives, the star may collapse suddenly and explode in a supernova event, releasing tremendous energy and scattering heavy elements across the galaxy. For now, however, Stephenson 218 remains one of the most impressive stars ever identified by astronomers. Its enormous atmosphere stretches across distances that dwarf the scale of our solar system. The star shines quietly within its distant cluster, thousands of light years away from Earth, a glowing giant hidden deep within the Milky Way. Discoveries like this remind us that the universe still contains many mysteries waiting to be explored. Each new observation reveals objects that challenge our understanding of cosmic scale. The largest stars ever discovered show us just how extreme stellar structures can become, pushing the limits of size that a star can reach before gravity and physics impose their boundaries. Yet even when discussing the largest stars, it is important to understand that size alone does not tell the full story of these cosmic giants. The mass, density, and internal structure of such stars reveal additional layers of complexity that help astronomers understand how these enormous objects can exist at all. When thinking about the largest stars ever discovered, it is natural to imagine that the biggest stars must also be the heaviest stars in the universe. Yet, the relationship between size and mass in astronomy is not always simple. A star can grow to an enormous radius, while not being dramatically more massive than other stars. This surprising idea becomes easier to understand when we consider the structure of red supergiant stars and the way their outer layers expand across space. Inside any star, gravity is constantly pulling the material inward toward the center. At the same time, the energy produced by fusion in the core pushes outward through the layers of the star. When these two forces balance each other, the star remains stable. For much of a star's life, this balance keeps the star at a relatively constant size. However, when the internal structure changes during later stages of stellar evolution, the outer layers can begin expanding outward. As the outer atmosphere of a massive star expands, the gas becomes more spread out. The same amount of material now occupies a far larger volume of space. Because of this expansion, the density of the gas decreases significantly. The outer atmosphere becomes extremely thin compared with the dense interior of the star. In many cases, the gas in these extended layers can be less dense than the air found in the upper atmosphere of Earth. This is one of the reasons red supergiants can grow to such extraordinary sizes. Their outer layers are not tightly packed like solid objects. Instead, they form a vast and diffuse envelope surrounding the dense core of the star. Gravity still holds the gas together as a single structure, yet the material is spread across billions of kilometers. The core of the star, however, remains a very different environment. Deep inside the star, the temperature and pressure remain extremely high. Fusion reactions continue producing energy through the transformation of heavier elements. These reactions create the radiation and heat that slowly move outward through the star, supporting the enormous atmosphere above. Even though the outer layers are diffuse, the total mass of these stars is still considerable. Many red supergiants begin their lives with masses perhaps 10 or 20 times greater than the mass of the Sun. Over time, they lose some of this material through stellar winds and expanding gas shells. Yet the remaining mass still creates strong gravity that holds the giant star together. An interesting comparison can help illustrate this idea. Imagine a balloon slowly being inflated with air. As the balloon expands, the air inside spreads out across a larger space. The density of the air becomes lower, even though the total amount of air remains similar. In a somewhat similar way, the outer layers of a red supergiant expand outward while becoming less dense. Because of this structure, a red supergiant may appear enormous when measured by its radius, while not being dramatically heavier than smaller but denser stars. Some smaller stars may actually contain more mass packed into a much smaller volume. The universe contains many examples where density and size vary in surprising ways. Astronomers studying these giant stars often analyze their spectra, the patterns of light emitted from the star at different wavelengths. By examining these spectral lines, scientists can determine the chemical composition of the star and estimate the temperature of its surface. Combined with brightness measurements and distance estimates, these observations help reveal the physical properties of the star. Through these studies, astronomers have learned that the largest stars in the universe often belong to the red supergiant category. These stars are in a late stage of their life cycles, where their outer layers have expanded dramatically. The enormous size we observe is therefore a temporary phase in the evolution of massive stars. Over time, the internal processes inside these stars continue changing. The core gradually produces heavier and heavier elements through fusion. Each stage of fusion generates energy in different ways, and eventually the star reaches a point where these reactions can no longer continue in a stable manner. When that stage arrives, the structure of the star becomes unstable. The balance between gravity and energy collapses, and the core may suddenly contract. This dramatic change can trigger one of the most powerful events in the universe, a supernova explosion that briefly outshines entire galaxies. Before reaching that final moment, however, the star spends a short period of its life as an enormous red supergiant, glowing quietly across vast distances of space. During this stage, the star may expand to incredible sizes such as those estimated for Scuti or Stephenson 218. These colossal stars remind us that the universe allows structures of astonishing scale to exist. Objects so large that comparing them with planets or even solar systems becomes difficult. Yet despite their immense size, they remain governed by the same basic physical principles that shape every star in the cosmos. Understanding the mass and density of these stars helps astronomers explain how such enormous objects can form and survive for millions of years. It also reveals why these giants eventually reach dramatic endings that scatter new elements across the galaxy. Those elements drifting through space may later become part of new stars, new planetary systems, and perhaps even the building blocks of life itself. In this way, the lives of the largest stars contribute to the continuing cycle of cosmic creation that unfolds across the universe. The enormous size of red supergiant stars raises a calm and fascinating question. Why do some stars grow to such incredible dimensions, while others remain relatively small throughout their lives? The answer lies in the slow evolution of massive stars and the delicate balance of forces that shape their internal structure over millions of years. Stars are not static objects. They change gradually as the fuel inside their cores transforms into new elements. At the beginning of a star's life, hydrogen atoms fuse together in the core to form helium. This process releases energy that travels outward through the layers of the star. For many millions or even billions of years, this hydrogen fusion provides a stable energy source that keeps the star in equilibrium. Gravity pulls inward while radiation and pressure push outward, maintaining a balanced structure. However, this balance cannot last forever. As hydrogen in the core becomes depleted, the star must adjust to a new internal structure. Without enough hydrogen fusion at the center, gravity begins to compress the core more strongly. The increasing pressure raises the temperature of the core until new fusion reactions begin involving helium and other elements. These changes inside the core cause a chain reaction throughout the rest of the star. The energy produced by the new fusion layers pushes outward with greater force. The outer atmosphere responds by expanding dramatically. Over time, the star grows larger and larger as its outer layers move farther into space. For massive stars, this expansion can become truly enormous. Because the star began its life with a large amount of material, the gravitational pressure inside the core becomes extremely strong as the star evolves. The resulting fusion reactions release tremendous energy that drives the outer atmosphere outward. This is the stage when the star becomes a red supergiant. During this phase, the star may expand to hundreds or even thousands of times the radius of the sun. The outer atmosphere becomes cooler as it spreads across a vast region of space. This cooling changes the color of the star to a deep orange or red tone when observed from Earth. The gentle red glow of these stars often makes them stand out clearly in the night sky. The structure of these stars becomes very complex during this stage of their evolution. Instead of a single region of fusion at the center, the star may contain multiple layers where different fusion reactions occur. Each layer produces energy in its own way, creating a structure sometimes compared to the layers of an onion. Deep in the center, heavier elements continue forming through fusion processes. Surrounding layers may fuse lighter elements such as helium or carbon. The energy from these reactions moves outward through the star, supporting the enormous outer envelope of gas that defines the red supergiant phase. Another factor that contributes to the large size of these stars is the relatively low density of their outer layers. As the atmosphere expands, the gas spreads out and becomes extremely diffuse. Because the density is so low, the atmosphere can stretch across huge distances without requiring enormous additional mass. The outer atmosphere of a red supergiant is therefore more like a vast glowing cloud than a sharply defined surface. The boundary between the star and space becomes gradual rather than sudden. This makes measuring the exact size of the star more difficult, because the outer layers fade slowly into the surrounding environment. Within this enormous atmosphere, giant convection currents transport energy outward. Hot gas rises from deeper layers while cooler gas sinks back inward. These movements create huge cells of circulating gas that can span enormous regions of the star's surface. Each of these regions may be larger than entire planetary systems. As these convection currents move slowly through the star, they cause small variations in brightness. The surface may appear brighter in some regions and dimmer in others. Over time, the star may also pulsate slightly, expanding and contracting as energy flows through its extended atmosphere. This stage of stellar evolution does not last very long compared with the overall life of a star. Massive stars burn their fuel quickly, and once they enter the red supergiant phase, the remaining stages of their lives unfold relatively rapidly. In cosmic terms, this period may last only a few 100,000 years. During this time, the star also begins losing large amounts of material through powerful stellar winds. Gas from the outer layers escapes into space and forms expanding clouds around the star. These clouds contain elements that were produced inside the star during earlier stages of fusion. Eventually, the core of the star reaches a point where it can no longer support the enormous weight of the outer layers. When this happens, the star experiences one of the most dramatic endings in the universe, a supernova explosion that releases vast amounts of energy and spreads heavy elements across the galaxy. Before that final moment, however, the star remains one of the largest structures in the universe, a glowing sphere of gas stretching across billions of kilometers. The red supergiant phase represents the moment when a star reaches its greatest physical size before its life approaches its dramatic conclusion. When we think about stars that are thousands of times larger than the sun, it might seem natural to assume that such enormous stars must live for extremely long periods of time. Yet the opposite is usually true. The largest stars in the universe actually live much shorter lives than smaller stars. Their enormous size and intense energy output cause them to burn through their fuel at a far faster rate. This surprising relationship between size and lifespan reveals one of the most interesting patterns in stellar evolution. A small star, such as a red dwarf, uses its fuel very slowly. The fusion reactions in its core proceed at a calm and steady pace, allowing the star to shine for trillions of years. These stars are incredibly efficient with their energy, and many of them will continue glowing long after stars like our sun have reached the end of their lives. In fact, some of the smallest stars may live longer than the current age of the universe itself. Massive stars follow a very different path. Because of their strong gravity, the pressure inside their cores becomes extremely high. This intense pressure raises the temperature of the core to enormous levels. At such high temperatures, fusion reactions occur much more rapidly than in smaller stars. The star, therefore, consumes its hydrogen fuel at an extraordinary speed. This rapid burning means that even though massive stars contain more fuel, they use it far more quickly. A star that begins its life with 10 or 20 times the mass of the Sun may live for only a few million years before reaching the later stages of its evolution. Compared with the billions of years that smaller stars can survive, this is a remarkably short lifetime. During this relatively brief life, the star evolves quickly through several stages. At first, it burns hydrogen in its core just like most other stars. Later, the core begins fusing helium and eventually heavier elements as the internal structure changes. Each new stage releases energy in different ways and causes the outer layers of the star to respond by expanding. This expansion is what eventually transforms the star into a red supergiant. The outer atmosphere stretches outward across enormous distances, while the core continues producing energy through increasingly complex fusion reactions. For a short period of time, the star becomes one of the largest objects in the galaxy. However, the processes occurring inside the core continue moving toward an inevitable conclusion. As heavier elements form through fusion, the reactions gradually become less efficient at producing energy. Eventually, the core may begin forming elements that cannot release energy through fusion. At that point, the delicate balance between gravity and energy can no longer be maintained. When the core reaches this stage, it may collapse suddenly under its own gravity. This collapse triggers an enormous release of energy that travels outward through the star. In a fraction of a second, the entire structure of the star is disrupted, and the star explodes in a spectacular supernova event. A supernova is one of the most powerful explosions in the universe. For a brief period, the star may shine brighter than billions of other stars combined. The explosion throws enormous amounts of material outward into space at incredible speeds. These expanding clouds carry heavy elements that were formed deep inside the star during its lifetime. Many of the elements found on Earth today were originally created inside stars that ended their lives in supernova explosions. Elements such as iron, gold, and many others were forged in the intense conditions of massive stars, and then scattered across the galaxy when those stars exploded. In this way, the lives of giant stars contribute to the chemical richness of the universe. The enormous red supergiants that we observe today therefore represent a short but dramatic moment in the life of a massive star. They are stars approaching the final chapters of their existence. Their vast atmospheres glow quietly across space, while deep inside the core, the processes leading toward the star's ultimate fate are slowly unfolding. Although their lives are short on cosmic timescales, these stars still exist long enough for astronomers to observe them and study their properties. By measuring their brightness, temperature, and size, scientists can learn about the physical processes that govern the lives of massive stars. Observations of stars such as Betelgeuse, Antares, Uye Scuti, and Stephenson 218 provide valuable clues about how stars grow and evolve. Each of these stars represents a different moment in the complex story of stellar evolution. By studying them, astronomers can piece together the sequence of changes that occur as massive stars move toward the end of their lives. Among all these giants, some stand out because of their extraordinary size, reminding us that the universe allows structures far larger than anything found within our solar system. These colossal stars quietly illuminate distant regions of the galaxy, while their internal processes slowly move them toward the final and dramatic events that will one day mark the end of their luminous existence. As massive stars approach the final stages of their lives, the calm balance that once held them together slowly begins to disappear. For millions of years, gravity and fusion existed in a delicate equilibrium, gravity pulling inward while the energy from nuclear reactions pushed outward. But eventually, the core of a massive star reaches a point where fusion can no longer continue in the same stable way. When that moment arrives, the structure of the star begins moving toward one of the most powerful events in the universe, the supernova explosion. Inside the core of a very massive star, a long chain of fusion reactions gradually produces heavier and heavier elements. Hydrogen first becomes helium. Helium later forms carbon and oxygen, and over time the star may produce elements such as neon, silicon, and eventually iron. Each stage of fusion releases energy that supports the outer layers of the star against gravity. However, iron represents a turning point in this process. Unlike lighter elements, iron does not release energy when it fuses into heavier elements. Instead, it requires energy to undergo further fusion. When the core becomes dominated by iron, the star can no longer generate the outward pressure needed to resist the crushing force of gravity. At that moment, gravity suddenly takes control. The core collapses inward at incredible speed, compressing matter into an extremely dense state. Within seconds, the inner region of the star contracts dramatically, while the outer layers begin falling inward toward the collapsing core. The process unfolds so rapidly that the structure of the star cannot adjust smoothly. As the collapsing core reaches an extremely dense state, the inward motion suddenly halts. The compressed core resists further collapse, and a powerful shock wave forms. The shock wave travels outward through the star with tremendous force, pushing through the layers of gas that had been falling inward only moments before. The result is a colossal explosion known as a supernova. The outer layers of the star are blasted into space at enormous speeds, carrying vast amounts of gas and newly formed elements across the surrounding region of the galaxy. For a brief period, the exploding star can shine brighter than entire galaxies containing billions of stars. Supernova explosions play a crucial role in shaping the universe. The material ejected during these explosions contains many of the heavier elements that exist in nature. These elements were created inside the star during its lifetime through fusion reactions and then scattered into space during the explosion. Over long periods of time, these elements mix with the gas and dust of the galaxy. Eventually, they may become part of new clouds of material that collapse to form future generations of stars and planets. In this way, the deaths of massive stars help create the building blocks for new cosmic structures. Many of the atoms that exist within our own planet were once forged inside ancient stars that exploded long before the sun was born. Iron in rocks, calcium in bones, and many other elements originated in the cores of massive stars. These elements were spread across the galaxy by supernova explosions and later became part of the material that formed our solar system. Red supergiant stars such as Betelgeuse are expected to end their lives in this dramatic way. Although the exact timing cannot be predicted precisely, astronomers know that these stars are approaching the final stages of their evolution. One day, the core of such a star will collapse, and the resulting explosion will briefly transform the star into an incredibly bright object visible across enormous distances. If a nearby red supergiant were to explode as a supernova, it could appear extremely bright in Earth's sky for several weeks or months. Historical records show that humans have observed supernova explosions in the past when stars suddenly appeared where none had been seen before. These events were once mysterious, but are now understood as the dramatic endings of massive stars. Despite the violence of these explosions, the life of a massive star spends most of its time in a quieter state. For millions of years before the explosion, the star exists as a luminous giant, slowly evolving while shining across the galaxy. During this time, the star may grow into one of the largest objects known in the universe. The enormous red supergiants that astronomers observe today represent this calm but temporary phase before the final transformation. Their vast atmospheres stretch across billions of kilometers, while deep inside their cores, the processes that will eventually lead to a supernova are gradually unfolding. Studying these stars allows astronomers to understand not only how stars grow to extraordinary sizes, but also how they contribute to the ongoing cycle of matter in the universe. The life and death of massive stars connect the formation of elements, the creation of new stars, and the evolution of galaxies. Among these immense stars, some have reached sizes so extraordinary that they stand as the largest stellar structures currently known. Observing these giants reminds us that even the most dramatic explosions in the universe begin with the quiet life of a single star, slowly evolving across millions of years. The existence of enormous stars, such as red supergiants, does not only represent an interesting stage in stellar evolution. These giant stars also play an important role in shaping the structure and chemistry of the universe itself. Although they live for only a relatively short time compared with smaller stars, their influence spreads across vast regions of space. Through their intense radiation, powerful winds, and eventual supernova explosions, they help transform the material of galaxies. Massive stars shine with incredible brightness because the fusion reactions inside their cores produce enormous amounts of energy. This radiation travels outward through the surrounding space and interacts with nearby clouds of gas and dust. When the powerful light from a giant star reaches these clouds, it can heat the gas and sometimes cause parts of the cloud to expand or move. In other cases, the radiation can compress certain regions of the cloud, helping trigger the formation of new stars. Because of this interaction, massive stars often act as catalysts for new stellar generations. The energy they release into their surrounding environment can reshape the structure of nearby nebulae. Some regions of gas become dispersed by the radiation while others collapse under gravity to form new stars. In this way, a single massive star may indirectly influence the birth of many other stars within the same region of a galaxy. The winds produced by red supergiants are also an important factor in this cosmic cycle. As the outer layers of these enormous stars expand, they release streams of gas into the surrounding space. These stellar winds can carry large amounts of material away from the star over thousands of years. The gas slowly spreads outward and mixes with the interstellar medium that fills the galaxy. Inside this gas are many elements that were created during the lifetime of the star. Elements such as carbon, oxygen, and other heavier atoms were produced through fusion reactions deep within the star's core. When the star releases material through stellar winds, these elements are carried outward into space where they become part of the surrounding environment. Eventually, when the star reaches the end of its life and explodes as a supernova, even more material is expelled into the galaxy. The explosion spreads newly formed elements across enormous distances. These elements enrich the interstellar medium and become part of future generations of stars and planetary systems.